everyone. Welcome to the 2020 December Tech Workshop, Microservices with a touch of CI/CD. My name is Mariona, and I will be the host of this Tech Workshop. Today we will go through the limitations of traditional backend applications and how microservices can help to overcome them. We will also learn the best practices for developing, testing, and deploying microservices, as well as the basics of CI/CD. Our speakers today are Colm and Marcello, backend software engineers here at TPI Software. They are experts in the fields of microservices and CI/CD, and we are very lucky to have them here with us today to share their knowledge and experience with us. Everyone attending today, both on and offline, will have a chance to win a special prize, a free JetBrains product license. We will raffle the license among all the attendees today, so please stay tuned until the very end. For everybody joining us online, please make sure that your microphones are muted so as to not disturb the presentation. If you have any questions during or after the presentation, please use the chat box. You can find the button on the bottom right-hand corner of your screen. We will answer all of your questions during the Q&A session after the presentation. Now let's hand it over to Colm and Marcello.
Hello, good evening everyone, or good morning depending where you're connecting from. My name is Colm, and today I have Marcello, and we are back-end engineers here at TPI Software. During today's workshop we will start off by talking about traditional back-end applications and the limitations that they might entail, and how taking a microservices approach can help alleviate some of those limitations. We will then talk about designing the microservices, testing them. We will then touch on some basics of CI/CD and why it's good to use it, followed by demos, and then we'll take some Q&A. So I will now hand over to Marcello, who will begin by talking about traditional backend applications.
Thank you, Colm and Mariona, for the introduction. I am Marcello, I'm backend software engineer, and I work on traditional backend application as well microservices. So I'm going to start talking about traditional backend applications. Traditional backend applications are standalone applications, and they typically contain business logic. They might expose a user interface, expose REST APIs. They may have typically a database, and they might use cloud services. Standalone applications requires typically a release every 6 months or longer, depending on the size of the application. There is typically downtime during the release, and the process to the deployment and the release usually involves some manual steps. Initially, traditional backend applications are easy to develop, since it's a single code repositories and a developer can see the whole code in its own IDE, can move through dependencies and modules easily. They are easy to change, since even a vertical change from the user interface, business logic, down to the database can be done in one time. They are easy to deploy, since it's enough just compiling the application, getting the binary, and deploying on a server. Easy to test. Once the application is deployed on a server, then we can run immediately an end-to-end test. And finally, they are also easy to scale. Usually it's enough having 2 instances running behind a load balancer to cope with the higher traffic. However, then the application grows, becomes more complex, and is no longer easy to manage. Let's look at the limitations of traditional backend applications. So the company is having success. There are more features required, more developers join the team, and at some point there are multiple teams that works on different modules of the applications. And we see here 3 teams, for example, one for the working on the order management, delivery, management team and the inventory management team. It's a single code repository, so at some point there will be some coordination issues of the teams working together on this code repository. Then the testing and deployment also becomes getting slower, since even for the small change we need to deploy the whole application and test it. And in production, ultimately, the application gets unstable. This leads to what is called monolith hell. That is a downward spiral that eventually ends with the company going out of business. So we can see the application gets more complex, there are new features that takes longer to implement, testing becomes harder, so there are more bugs, and then developers find workarounds and patches that leads to an application even more complex, and so on. So how to deal with these issues? Now we're going to introduce microservices, the ones to help tackle these issues. What are microservices? Microservices are small independent services that have their own data model or database, and they communicate via APIs. Very important thing about microservices is that they are independent. So the development, deployment, testing can be done independently per service. One very important thing to mention about microservices is that they address non-functional requirements, that is scalability, independent development, deployment, and testing, as we said. And they do not address functional requirements, since a use case, when we need to implement a use case, can be implemented with any architecture. We can even write the whole code inside a single function, and we can implement the use case. The benefits: being independent, they are easy to adapt, easy to adopt new programming languages. New features are developed quickly. It's possible to do a fine-grained scaling. You can scale a single microservices independently. Better fault isolation. A bug in a microservices doesn't lead the whole application to crash. And all of this enabled what is called DevOps. Talking about DevOps, this is what the organization would look like adopting microservices. So it's not just an application change, but it's an organization change. There are now the teams, they work on their own service, which, for example, the order management works on the order service. Each service has its own deployment pipeline and is deployed independently. Additionally, the organization can scale by adding teams and not just people. Each team has a clear responsibility and ownership of the microservice. All of this it's under the name of DevOps. Here in this slide we can see clearly the better overview of the benefits of microservices. They improve the maintainability, meaning that here a single microservice is easier to develop for a small team rather than having the overview of the whole application. Scalability, fine-grained scalability, independent testability, and deployment. So what is the difference between service-oriented architecture and microservices? Those are similar architecture patterns. We can identify in three areas: communication, data, and size of the service. For the communication, service-oriented architecture typically use heavyweight protocols like SOAP and SOAP, and the smart pipes like Enterprise Service Bus, while microservices use more lightweight protocols like REST, gRPC, and the less smart pipes like simple queues or topic. Data, typically for SOA architecture, there is a shared data model or database among all the services, while for microservice, it's a database per service. The size is also typically larger in case of the SOA compared to microservices, as we see from the image. Does microservice always make sense to adopt? Fortunately, the answer is no. There are a number of reasons that we need to consider when adopting microservices. API calls goes through typically through the network, so it's slower and more complex than a simple method call. There are partial failures in networks. Network gets slower, packet loss, and so on to handle. And ultimately, we have a distributed system rather than a single standalone application. That means you need to do service discovery, find the right microservices at the right moment, log aggregation. Now there are more than one log file instead of a single one. Distributed transactions, a transaction that goes spanned through different microservices, monitoring, and so on, analytics. When doing microservices, there is a risk to decompose excessively the application. Testing and deployment gets harder, not independently, but end-to-end testing, and can be, finally, also more expensive. Let's look at what are the best practices about designing microservices. What is a service? A service is a standalone component, independently deployable, that provides a useful functionalities. Service provide commands, queries, and events. Commands are to manipulate the resource of a service, create or delete a resource. Queries are to read and filter those resources, while events are notable events that when a resource changes or is updated, that needs to be sent out. What's the size of a microservice? How big should be a microservice? At the end, it doesn't really matter. One team per service is usually okay. So how big should be the team? There is a popular quote from Jeff Bezos that says, if you can't feed a team with 2 pizzas, it's too large. So we can use this as to general measure for a team size. And it's important for a team that should require minimal collaboration with the other teams in order to be independent. When designing microservices, the suggested methodology is to use domain-driven design. That is, and domain-driven design says the application structure should match the business domain. Here we see a list of steps that can help in designing a microservice using domain-driven design. Identify system operations, identify services, and define service API and collaborations. The system operations start from the requirements. We get a high-level domain model, and I need to define the system operations, which are commands and queries, let's say. Identify services by decomposing the domain into different services, and finally, as we said, we map the system operation to the services. Here we see an example. This is an example of business domain logic design. Traditionally it's done like so. And what we see is that a single domain model composed by different classes. And in this case, the application of a restaurant where the customer can order to this restaurant. And the first thing we see is how to divide these classes into microservices. So there is a lack of boundaries. We don't see clearly how they can communicate with each other. In a microservice design, this would be the outcome of the design. And there is a concept of an aggregate that has a clear boundaries. We see that an order aggregate, a restaurant aggregate, and a customer aggregate. One important thing is to identify the root of the aggregate, and the system operation are allowed only on the root of the aggregation. So this let us clearly see the boundaries in the domain model, and ultimately we will create microservices based on the aggregate. Following, there is an API first approach when designing microservices, and this is very important when implementing a new service. since we need to agree first on the API and then focusing on the implementation of the service to maximize the team collaboration. When there are API changes, then it's important to do only backward compatible changes, so adding, not removing, and using semantic versioning with a major, minor, and a patch subversion. And to specify the version can be used the path or in the message. Regarding the communication between microservices, there are two different approaches, synchronous and asynchronous communication. Synchronous communication is a one-to-one, a request and a response is expected. Asynchronous communication, one-to-one, there may be a request and then is not blocking, and a response will be handled later. One-way notification when a response is not expected, and asynchronous communication can be one-to-many, publish and subscribe, or publish and synchronous response. There are different communication technologies to implement such two approaches. Synchronous, we look at REST and gRPC. Asynchronous, we can look at the standard AMQP. Regarding message formats, can be human readable, like JSON or XML, text, and binary. For example, Avro or protocol buffers. Synchronous communication limitations. What happens when a service is unresponsive? In this case, we can use timeouts like circuit breaker. Or there are too many requests. We can implement throttling. So in order to limit the number of requests, to find an instance, we need some sort of a service discovery, which can be delegated to a specific tool like Eureka, or we can use the built-in service discovery in Kubernetes or Pivotal Cloud Foundry. Regarding asynchronous communications, there are three types of messages. It can be documents, only data, command, like RPC call or a normal request, and an event. They divide in a broker-based or brokerless. Typically, asynchronous messages involves a third party, which is a broker that receive the message and deliver to the assigned consumer. And there are different technologies for doing so, ActiveMQ, RabbitMQ, and so on. They are typically, they implement message buffering, and they let the architecture be loosely coupled. Or there are brokerless approach, like ZeroMQ, which has a better latency. When we decide about the broker, message broker, there are trade-offs to consider. What are the supported programming languages? If it implements a standard or not, if it keeps message ordering, persistence, scalability, and what is the latency. When asynchronous communication is to prefer for microservices, or let's say to use it in general as much as possible, since it improves high availability. As we see from the picture, all the services are not, all the requests are not blocking, and so this highly improves the high availability. The domain events are notable events upon a change to the aggregate, and they can be used by other applications, for example, to get a notification and to do some updates for monitoring or analytics. When designing microservices, there is often the need to do some aggregation, and this is called query composition. In this case, we see there is a front end and two services, order service and delivery service. The front end wants to show an overview, order overview, that includes the order ID, the total amount of the order, and the status. This information comes from the order service regarding the ID and the total, while for the delivery service we need the status. So the front end is going to send two requests, one to the order service, one to the delivery service, does the aggregation, and can display the overview. This is the first approach. The second approach, we want to delegate this aggregation to a service in order to leave the front end simpler. So there will be only one API exposed by the order service that creates this aggregation of the information required and returns it to the front end. Now this is a better approach since the front end now it's simpler. However, the order service needs to know the details of the delivery service. So the additional approach is to extract this logic into its own service, in this case order overview service, that provides only one API to the front end and does this kind of aggregation. This is a final approach that it's more independent. However, it doesn't cover all the cases. For example, this case of this query. In case of a complex query, like show all the delivered orders in 2020, the order service, we can retrieve all the orders of 2020 from the order service. However, we don't know which are delivered and not. So we need to request the delivery service about the status. And this involves sending many requests to the delivery service, and so in general can be a bottleneck. So in this case, there is a common pattern called command query segregation pattern that can help in this case. There is the order history service that will not request this information on demand, but keeping a state of the overview we want to show. And this state is updated every time an order service creates a new order, or the delivery service sign that an order has been delivered. And whenever a front end requests this information, it's already there. Regarding external communications, for traditional application, there is a Monolith application that we see on the right, and external application like the browser, mobile apps, or third party access directly the Monolith application, typically behind a firewall. How to set up this with microservices? Microservices, suggested pattern is the API gateway. That is an additional layer that receives the request from the browser, mobile app, and third party, and routes those requests to the relative service. As we see, the gateway is between the external clients and the microservices. Additionally, the API gateway can be used for protocol translation, composition, like query composition that we've seen before, authentication, authorization, implementing throttling, and so on. Popular tool for Java application is a Spring Cloud Gateway. Testing microservices. Now we're going to look at the best practices and the suggested practices for testing microservices. Regarding tests, there are three types of tests. It's important to mention: unit test, integration test, and end-to-end test. As we see from the image, we order these types of tests based on how quick hard they to run, test on top as low and expensive, while tests on, at the bottom are fast and cheap. Unit test, the properties of the unit test, they should run quickly and able to run anywhere. Regarding the controller layer of our application or microservice, it's important to mock the service, which is the dependent layer of the controller layer, in order so that we can run unit tests quickly. And in Java, we can use Mockito for doing so, or using this annotation WebMC test and mock MVC. For the service layer, the dependent layer is typically the layer below, that is a repository layer, which can still be mocked. using other type of annotations in Java, like inject mocks and mock. And finally, the repository layer. The unit test should run quickly, so we don't want to spin up a database. And for this, in this case, we can use an in-memory database. Integration test is that we want to verify that a service can interact with the infrastructure. So there are two options. One is to deploy everything and test. However, this is slow and expensive. The other approach is to mock the dependent service and to run a unit test. However, this is not a realistic scenario in production. So which approach to use between these two? The suggested approach is actually the consumer-driven contract testing. It is something between, for example, for the controller layer, the dependent service, we provide a stub, like the service B stub and the service D stub, so that these stubs are going to simulate the APIs of the dependent service, and we can run the integration test independently. One tool for doing this is a Spring Cloud contract. Integration test, repository layer. We can pay the price of spinning up a database. However, to make it quicker, you can use a Dockerized database. And finally, the end-to-end test. In this case, we are going to deploy all the microservices in the full application, and we run an end-to-end test. Can run manually or even by the testers, or can be also automated using tools like Gherkin or Cucumber. Okay, that's for me, and I'm going to hand over this to Colin.
Thank you, Marcello. So I will now talk about what is CI/CD. So CI/CD, the continuous integration, is essentially the practice of automating the integration of your changes, and that's merging your code into a shared repository, building the code, checking that there's no compile issues, and then testing the code that that code has not broken any new functions. And continuous delivery and continuous deployment. So there's two types of the CD. So there's a famous quote that the ability to get changes of all types, including new features, configuration, bugs, and experiments into production, into the hands of users safely, quickly, in a sustainable way. And with continuous delivery, the software is always releasable, and you can decide when you want to release it, daily basis, weekly, fortnightly. It's whatever suits your business requirements. And continuous deployment takes this stage further. This is where it will automatically deploy your software into your production environment. And this is usually if you have higher deployment frequencies and if you want feedback from your users. So this illustrates the differences. As you can see, the deployment to production stage is a manual for the continuous delivery. Normally, teams may start out off with a continuous delivery until they build up confidence in their CI/CD pipeline, and then they will transition to the continuous deployment. To do CI/CD, there is many tools, and it really depends on your needs. Some are open source, some are not, some cost a fee. Some manage at the repository level, and others pull the code and then run the build. Some can be on the cloud, but some also can be on premise if that's a requirement. And each one comes with its own plugin, so maybe there's a certain plugin you need for your application, so you might be swayed towards that particular tool. And this is an example. So this shows that the developer can push code. We have Bitbucket as an example. Jenkins will then pull that code in. We can do a build with Maven, run the JUnit test, scan the code with SonarQube, build a container with Docker and push it to a container registry such as AWS, and then deploy it straight onto your Kubernetes dev environment. For the UAT, you may have Jenkins create a release ticket, so it will do the continuous integration part, but then it will create you a ticket with the bill of materials, and it may be triggered by apps to go onto your UAT environment. And for the production, you can tick that same ticket that contains references to your bill of materials, such as your Docker image tag or your Git commit ID, and you can pass it, and then it will get deployed into your production environment. So there's many benefits of using CI/CD. We have building the code, so this ensures that someone hasn't prevented other developers from building the project. Testing, so as well as your new feature is behaving as expected, you have not broken a feature that was done by another developer. The coverage of the code, so whenever you check in your code, there should be adequate testing done, so there's no part of what you did that was overlooked. And scanning the code for vulnerabilities such as SQL injection, technical debt, and checking the style. So it's good to adhere to a defined standard with the code, such as spacing and parentheses if they're on the method line or they're below it. And this keeps things nice and clean for other developers. So once you have your CI/CD pipeline, how do you measure the success and things to look out for? Well, the time to production should be less, because you should be able to get feedback if your code's working and if it's releasable. The quality of your code, you should notice it's more clean because of the style and the checking for vulnerabilities. The defects raised in production should be down. If you see your defects are becoming more, then your integration part of your CI pipeline is not really covering enough, or there's something happening that should be looked at. The time that the pipeline is broken, once the pipeline is broken, the feedback and what went wrong with the pipeline should be enough information that developers can look at it and get it fixed as quickly as possible. The downtime during deployment, so whenever you automate your deployment, there's less chance of a failure happening, because it's not human, there's no human error. Usually you have a runbook on how to deploy, but if that runbook was automated, then you're taking out the human error factor. The time the defect is raised to when it's resolved should be minimal, because the pipeline helps you speed up your development and release cycle. And you should try and keep your regression test duration short. This is because if you have a big long regression test that takes like an hour, then if it fails, the developer will get the feedback that maybe their attention has gone somewhere else. But with microservices, you can really target your testing. Normally with a monolith application, you work in a function, but your regression test just might be to start to run the test in a sequential order that's always the same. But with the microservice, you know what part of the system you worked on, so you can run that first, because that's likely where the issue may occur. And if we look at the deployment pipeline, there can be many flavors. It really depends on the type of project, but usually there's a the stages are mainly the same, where you build your project and you check it out. So it may be a Git repository or a subversion. You build it, Maven, Gradle, if it's Java, or if there's no JS NPM. Your testing could be JUnit or TestNG. You analyze the code, the SonarQube, and you can use some check style tools. And Docker can push it to multiple containers, such as GitLab registries. AWS is an elastic container service, and we also have Docker Hub. And the deployment too can be deployed in multiple places, such as the Amazon's EKS, Google's JKE, which is Google's Kubernetes engine, or any other container service. So we're now going to take a look at a demo. For our demo setup, we created 3 Spring Boot microservices and also a client UI. We package these into Docker images, and then they're deployed on Kubernetes, and we use Minikube. There's going to be show 4 demos. So the monolith approach, and then the microservice approach. And then we're going to demo the microservice failing, but the client can handle it. And then we're going to test the high availability of microservices. And this is the demo outline. So you can see this is our UI. We have the message service, and we have the balance service, and then we have the transaction service. The transaction service, when you scroll, issues another request for pagination to fetch the next set of data. And also we have deployed Prometheus and Grafana. So Prometheus pulls metrics from the application, and then Grafana reads those metrics and makes a nice graph. So you will see that in our application. For the first demo, this is the Monolith approach. So as you can see, all our functions are inside the one application. And whenever the application reaches higher CPU usage, even if there's only really been a single function being utilized, the whole application needs to scale to be able to support that. So now we can see the demo, and we can see that we are using the transaction function, but we only have one service, which is our Monolith application, that contains the balance and contains the message service. And as we're using this transaction service, one function of this application, you can see on the right that our CPU has spiked. And at some point when multiple users come on and use this, you're going to have to scale your full application just to manage this, and it's only one function that's been used. So now if we look at the microservice application approach, where we have split the balance service, the message service, and the transaction service out into their own microservice, once the transaction service or the message service gets used more, they can scale independently. And I should point out, we use Lens in this demo, and it's an open source project, and it organizes the Kubernetes objects, such as the nodes, the namespaces, services, deployments, stateful sets, and pods. So during the application, the demo, we will stop the pod using Lens, and it's essentially just an IDE for Kubernetes. So here you can see that our services are deployed, and we have the transaction service. So now the green line is the client, and the orange line is the transaction service. So as you see, the client will do an initial loading of the data, but really the load is on the transaction microservice. So now, as this function gets used by more and more users, we don't need to scale the full application. We only need to scale the transaction service. For the next demo, I'm going to show how a microservice can have an issue, and it shouldn't affect the other functionality in the application. So in this demo, we will stop the message service, and you should see that function will just go offline. So maybe you take it down for maintenance, or you're doing an update, or it has some error and it falls over. So we have an auto refresh of the application, and you can see at the top right we have the message icon. So now once we stop this service, it's no longer available, but the message icon is now gone, but we can still retrieve our balance, and we can still retrieve our transaction. So the user can still use those parts of the application. And once the service is recovered, we can see that it's now come back online. For the final demo, we will show the high availability. You can have multiple replicas of the microservice. As more users use them, they can expand, and you can also have them there for fault tolerance. If one falls over, the other is there to handle the load. So in this one, we will stop the balance service, and we will see that it can still function. And then for demo purposes, we will actually stop the 2 microservices, and you can see that actually there is a difference in the behavior whenever you have a complete failure of the balance service. So here now we will stop one of the balance services, and as you can still see, we are still able to retrieve our balance. But now, as we stop the 2, just to show for the demo, you can see that the balance will become unavailable. And once those services recover themselves and come back online, then we should see our balance return to the application. And although the balance service is offline, we still have our messages and we still have our list of transactions. So there now our balance is returned. So to summarize, we showed the monolith versus the microservice and how you can scale at a microservice level and not a whole application level. When a microservice goes offline, it may have failed, it may be taken off for maintenance, that other parts of your application can still function. The application doesn't go down completely. And when a microservice suffers a failure, multiple replicas can be used to take the load. And this is where it's really load balancing from the microservice level and not load balancing from a monolith application level. So in TPI, there's been some applications that have been done that have gone to production. So these are an example of a blockchain-backed application for a PowerPoint system. So this had microservices that were developed in different languages, Go and Node.js, for example, and it was the deployment shared configurations, and the deployment was automated on a pipeline using GitLab. So the blockchain was like a Hyperledger, and we have our CouchDB or peers, etc. And the other application was a mobile app for credit card management. So this was an application that used the microservice architecture. It was decomposition based on business functionalities, and the pipeline was automated using Jenkins. And doing this, where the software was able to release 3 times faster than previously. And the last one was a mobile app for digital banking account. So again, it was a microservice architecture, decomposition based on the channels, the business and the common functions. And this application had more than 200 APIs. If you would like to read further, we have some references: microservices patterns, examples in Java, monolith to microservices, evolutionary patterns to transform your monolith, the DevOps handbook, and we have speeding up deployment to production with CI/CD with trunk-based development. And we also have transition to microservices, Strangler Fig pattern, and those are available on the TPI University. So, thank you. We would now like to take any questions that you may have.
Yeah, I have a question. You showed a graph of the microservices CPU usage before. What other data can be retrieved?
Yeah. So the question is we showed the graph of the CPU usage of the microservice. So what other data is available? So we use Prometheus, and Prometheus exposes a number of metrics, such as the memory. And in our case, it was a Spring Boot, so you had the JVM, such as garbage collection metrics, the thread pool, the number of classes loaded. And you can also add in your custom metrics with Prometheus if you wanted to. So you can count how long a method takes in your code. You can count how many times a function is called. And you can also log events, such as how many times was an information message logged or an error message logged. And with Grafana, use charts such as the bar graph, the line graph, and you can also use a gauge such as if you have a bounded value, say like a percentage is 100%, then you can use those such metrics to display your dashboard in Grafana.
Yeah, one question. So just now Marcelo has stated that by using microservices will be much more complex. So I would say, like, would you recommend by using microservices for like a small system or a small project?
Okay, so the question is by using microservices, we are going to add a complexity. So does adopting microservices make sense for a small project? So as you said, adopting microservices is we are gonna, let's say, pay the price of the complexity, and we need to check if this price, if this complexity is worth it. Usually for a small project, typically we want to deliver a new feature really fast. We want to see if the project works. We want to see case of a POC, proof of concept. So there is really the need to be fast and quickly. In that case, using microservices is not really recommended, since there will be for sure some time spent in setting up, designing, adding service discovery, log aggregation. So all this kind of complexity will take more time. And so in this case, if we want to use a standalone application, would be the recommended way, I would say, for small project to start with a standalone application. Like for the reason I outlined at the beginning, we're going to have easy to develop, since it's a single code repository, easy to change, easy to deploy. We just need to deploy on the server, and it's running and easy to test. Running an end-to-end test would be easier in a standalone, rather than setting up all microservices. And for small projects, yes, as I said, we really care usually about delivering the feature faster. So that maybe adopting microservice can be done in a later stage. And one more thing that I would like to mention is that when developing a standalone application, we should try initially to design in a way that moving to microservices in a later stage would be easier. So we're going to design the application already with a well-defined context and define domains. We can divide these domains in packages. So we don't need to create microservice. We can define this domain object inside the packages, so that it will be easier later to move to microservices when the project is getting too large and we are facing the issues that we saw before. So then maybe could be a good indication that moving to microservice, it's worth, let's say.
Okay, some questions online. Okay, so Pack.js is used for microservices integration and testing. Do you use this? If so, could you give me some pointers? Do you use it?
For
Pack.js?
Pack.js, as a developer here, for example, at TPI Software, so far we focused on Java. And as an integration test, I have some experience with Cucumber and Gherkin. So for this integration test, I cannot add more details about Pack.js because I personally haven't used it personally. However, there are some general indications in the slides. Thank you for the question.
Okay. How do we address latency between microservices I mean, if one microservice is causing latency and affecting the performance, how to address this? Well, I would say it would depend on if it's a response that you need straight away, like you do the REST and you need the data that it returns, otherwise you could be added to a queue. But you can also scale a microservice and give it more memory and CPU, I guess, to try to address that. Do you have any pointers?
Regarding latency on large systems, I've seen that there are some tools that can be used to address if there is a immediate increase in the latency. For example, this system are called tracing systems that basically instrument the request so that it's possible to see each request, how long it took for each microservices, because a request is going through many microservices in application. And so through tracing systems is a way, for example, to address these issues. And once you know the time of the request for each microservices, you can maybe through the help of a user interface, you can say see where is the increased latency. However, then to have a better look, there are also the help of monitorings in this case on the machines where the applications is running.
Question. From your experience using pipelines for production releases, have you noticed any major differences between GitLab versus Jenkins versus any other platform? What considerations would you make when selecting the CI/CD platform? So, I guess with the CI/CD tools, there's plugins available for each one, and normally it depends on what application you're trying to make, if there's a particular tool that you want. But I notice on the GitLab, you can have more control at the repository level, meaning that you can kind of reject a commit before it gets actually in. But with the Jenkins, it just pulls it in from your repository, so at that point it's already in there, it's already committed. I would say, yeah, the considerations is usually just from if you want it open source, if you're okay with on the cloud, you have Bitbucket Cloud. But if you want it on premise, then yeah, like tools like Jenkins would be available for that. Any questions on site?
I have a question. How to decide when to use continuous deployment over continuous delivery?
Okay, so the question is when to decide to use continuous deployment over continuous delivery. So usually whenever you have confidence in your pipeline, then continuous deployment can be good to help get out to your users quicker to the market. And there might be some cases that maybe you use your customers as your testers. For example, there's some companies that have a beta test program, and in your application you may have a feature flag that's really, you can push out your new features that's only available to that subset of users, and you can have them tested at scale, more users, and get the feedback, and then open it up then with your feature flag. So I would say that will be the main difference. But I would say to do that, you have to have confidence in your pipeline that it's going to catch the issues and it's really being battle tested. Yeah.
Okay. No further questions. So we're going to hand over to Mariona. Thank you.
All right, thank you.
Okay, thank you Colin and Marcello for such a great presentation, and thank you everybody online and on-site for attending our Tech Workshop today. We hope that you learned some useful information about microservices and CI/CD. Before you leave, please click the questionnaire link on our chat, which our Tech Workshop assistant has just sent, or you can scan the QR code on your screen and help us fill out the Tech Workshop questionnaire. We will send out the slides and the video recording of today's presentation to everybody who submits the questionnaire. We would also love to have you follow us on Facebook and LinkedIn so you can stay updated on our future events and the latest news, as well as job openings, as we are hiring talented developers and engineers. You can find the links in the chat box as well. As for today's special prize, we will raffle a free JetBrains product license among all of you who attended today, both on and offline. So we will be contacting the winner by email, so please keep an eye on your mailboxes. Thank you once again for joining our 2020 December Tech Workshop today, and we look forward to seeing you again in the future. Bye everybody.